All right, so let's get going on today's class. And before we get to the statistics of today's class, I mentioned in an announcement on Canvas that we have two extra credit bonus point opportunities that I'm going to start rolling out at this point in the semester. And I'll just give you a brief announcement and explanation of what those two are. They're completely optional. I am still in the process of working out all the details, so I don't know exactly how much they're going to be worth. I'll figure that out in the next few days. But these are bonus opportunities that'll help you improve your grade a little bit in this course, but also will also have other benefits to you even far beyond this particular course. So, what are the two opportunities? Well, the first one is a social media professional development series of steps and to help you develop a professional social media presence. So why would we even consider doing this? Well, very importantly, social media is becoming something that is no longer just for entertainment, but more and more professionals are using it, and importantly for you, when you go to apply to grad schools and when you go to apply for jobs, more and more professional places are using it. So I found research on this, and as it turns out, 70% of employers, so 7 out of 10 employers, will look at your social media profile. So 70% of the places where you apply to, be it work or grad school related, will take a look at your social media profile. So it's important to know what they're actually looking for. So when they look at your social media profile, this one is one of the key things we're going to try to develop. 61% are looking for information that supports your qualifications. So for example, if you're going to grad school, and you have your personal statement, and they say, why do you want to become a psychologist? And you say things like, well, I'm very interested in psychology. I've ever since I was young, I've always wanted to be a psychologist. They will look at your social media profiles for postings about psychology, for proof of your qualifications. So 61% will look at your profile for information that supports your qualifications. 50% we'll just look to see if you have a professional online persona at all. So do you have a professional presence on social media, or is it just all vacation pictures and cat memes? 37% will actually take a look at what other people are posting about you. So we are also going to try to develop your network around the idea of amplification as well. And then this one, you probably have intuited from what's been happening in the news. 20% of employers will look at your social media profile looking for any reason not to hire you. So we are also going to go through how to develop this social media profile of yours, a professional social media profile, so that those 20% will not find any reason. And in fact, they'll find reasons to hire you rather than to avoid you, to accept you into their graduate school program rather than to say no. So that's the why of what we're doing here. It's not for the course. There's not going to be any statistics to this, but it is an important thing to start building for your aspirations after you graduate. So why else are we going to be doing this? This is going to be a little bit more immediate in terms of its benefits to you. So one thing that you will have when you start developing your social media profile professionally is you will be able to connect with your community. So this is very important in this day and age to get connected into a network. So we're going to use this to connect with your fellow students, either here at IUSB or other students in other programs around the country, around the world. So you can connect to your fellow students, build that community. You can build a community with psychologists. You can start getting to be known by other psychologists, other professionals in your area. So this idea of connection is becoming more and more important. It's something that can give you a great advantage once you get graduate, but also even before then in terms of helping you out with your coursework here, seeing what other students have gone through, being able to turn to your community for suggestions. All of this can come with a well-developed social media profile. So we're going to roll this out. We're going to start out very slowly on this. So for your social media professional development assignment number 1, and this is completely optional, right? So this is for bonus points in this course. The first thing I want you to do is I want you to sign up for a professional Twitter account. Now the reason that we're using Twitter is that academics use certain social media platforms. Employers use certain social media platforms. They're not the same in terms of the ones academics use and the ones that employers use, except for Twitter. Twitter is very highly used by both academics and both employers. So if you were strictly going for employers, that would be LinkedIn. If you're strictly going for academics, they do a lot of their posting on Instagram and YouTube. But Twitter is high up for both of those, so it covers all those bases. It's a great way to start. So the first thing you want to do is sign up for a professional Twitter account. So if you've never signed up for a Twitter account before, you can follow the links there or just Google Twitter, and you can sign up with Twitter, and welcome to the world of tweeting. If you have signed up for Twitter before, if you already have a Twitter account, and you have not been using it for professional posting, then what you want to do is you want to sign up for a second account. So for example, I have a personal account where I will post things about hobbies, about interests, vacation reactions, how much I love the particular movie, all that kind of stuff. That goes into my personal one. My professional one is about psychology, it's about education, it's about research. It's about the Undergraduate Research Committee Conference. So make sure that if you already have one that has been used for personal use, just get yourself a second account, and that will be your professional presence. All right, so that's step 1 of this. Second step, send me your username via Canvas Messages. So in Canvas Messages, just let me know what your username is. Occasionally it's quite obvious, sometimes not so much, so just to make it easy for me to track who's accomplished this, send me your username via Canvas Messages, and then finally you want to follow me so we can start connecting everybody to each other, and you're going to follow @Paladinsane on Twitter, so that's @Paladinsane, Paladinsane, and that's my professional Twitter handle. So again, we're going to be doing this. Again, it's important more and more. This is an older statistic. This is a couple of years old. I'm sure by now it's even higher. They do look at your social media profile. So for the future, you'll be prepared. And in your current times, right now, it'll benefit you by connecting you to your fellow students and being able to connect yourself to your fellow psychologists. And it's just it will benefit you in so many ways. So hopefully you'll climb on board, and we'll get everybody developed in their social media presence. So for this first part, the due date is going to be Monday, September 30th at midnight. So if you want to earn points towards these bonus points, just make sure that you do those very brief minor steps before Monday, September 30th. Be sure to send me your username. I will make a record of that so that we can start again connecting each other in this assignment. Any questions on this? Yep.
Will you be posting that on Canvas?
So this is available, these slides are available on Canvas? Is that what you were?
Yeah.
Yep, yeah, so these slides are available on Canvas. And there's now a new folder for social media professional development that'll have these slides and any future slides that are coming up. Any other questions? All right, so that's opportunity number 1. Opportunity number 2 So your second opportunity to earn bonus points towards your final grade, and this one also has side benefits to you as well, is what I'm calling the Innovation and Suggestions Weekly Survey. So each week, I'm going to be asking you for suggestions, for innovations to improve the course. So why are we doing this? Well, one of the things you always try, or at least I always try as an educator, is to innovate and improve. The way to make sure that your course is not doing well, not fitting the needs of your students, is to teach the same course year after year after year. So students change, ideas change, techniques change. So what we're trying to do is we're trying to innovate and improve this course. This will also be a nice experiment. I'll admit I haven't tried anything like this before, but it'll also be a nice experiment to give you a little bit of say and a little bit of power in terms of how a course is designed. So this is your opportunity to basically take some agency and take hold of your own pathway in your learning career. And also, once again, we get to this idea of we're building a community. So if you participate in this, and we are part of building this course together, we are part of this educational process together, and just the idea of kind of taking in from other people and hearing other people's voices, I think, is probably going to be very beneficial. For all I know, this is going to be a horrible idea. This is the first time I'm trying it, but again, if you're not willing to put yourself out there, you're not going to be able to improve. So, what is this all going to entail? Well, the way that we're going to do it is we're going to have anonymous weekly surveys. So I've already sent out an announcement in Canvas that has the link to this week's survey. And what the survey is it's basically going to ask for your innovations and suggestions for how to improve the course. So any ideas that you have, you might not have any for that week, that's fine. You might have a lot for a particular week, that's awesome as well. Just anything you can think of that would improve your learning experience, would improve this course, as wacky and wild as it might be, or as tame as it might be, whatever it is, this is your chance to have your say. What I'm going to do is I'm going to go through the suggestions, and I'm going to post those top 5 every single week on Twitter, and then you will be able to vote for the one that you like the best, and you'll be the ones that decide. This is an amazing suggestion. This is a great innovation, and this is going to be where I'm going to use a little bit of that competition drive to get people involved in this. There will be bonus points awarded for the writer of the top voted innovation and suggestion for each week. So each week somebody will earn bonus points, and again, I'll figure out exactly how many bonus points towards their final grade if their innovation or suggestion is considered the top one for the week. Now, you might be sitting there and thinking to yourself, well, that's great, we're going to get bonus points, but I thought you said it was anonymous. So how are you going to figure out who wrote each particular innovation? So first off, it's very important that this is anonymous, because I do want honest feedback, I do want honest ideas, and I don't want anybody to censor themselves and think, oh my gosh, I don't want to say this, because maybe Professor Udich will take it the wrong way, right? So I am looking, criticism is welcome. I am looking to improve this course overall. I have gone through peer review processes, so I know, I've developed a little bit of a tougher skin, but I do want you to feel safe doing this, so it is going to be completely anonymous. The way that we're going to track what the suggestions are, in Canvas, in the files, you will see an Excel sheet that is a random number generator. So that is your suggestions random number generator. And if you open up that sheet, go to an empty cell and just hold delete, it will generate a random number between, what did I set it at? Between 1 million up to 1 billion. All right, so it'll generate you a random number. What I want you to do is generate yourself a random number, write that number down somewhere in your personal records, and then if your tweet is the top tweet, is the top suggestion, sorry, if your innovation is the top innovation for that week, and you feel comfortable coming forward and saying, yes, that is mine, you can just email me your random number. I will have that in the record, so that is in the survey as well. The very first question is, what is your random number? The next question is, what is your innovation? So make sure that you enter the random number in the survey, make sure that you record it for your purposes, and then if your suggestion comes out on top, and again, you feel comfortable saying, yes, I will take responsibility for that, I would like to earn those points, just email me through Canvas messages. That was my suggestion, here's my random number, and I will be able to award you the points. Yep.
Should we stick to the same random number, or do we have to change it every time?
I would change it every time, you know, just because it's a cool feature, so you can just hold delete and watch the numbers fly. But either way, I think it'll work. Any other questions about that? All right, so make sure that you do that. That's how you're going to get the bonus points for writing that top innovation and suggestion. And again, the bottom line is we are trying to innovate, we are trying to improve. The best way to have ideas, great ideas, is to have lots of ideas. So even if you think it's ludicrous or it's crazy or it's, you know, has no chance of succeeding, if you have that idea, put it down. Who knows, right? Some of the greatest ideas, I'm sure people thought they were crazy. So the links are going to be available weekly in Canvas announcements. So there are going to be different surveys every single week. And the due date for this is going to be every week by Friday at midnight. So sometime between now and then tomorrow at midnight, if you have an idea, if something came up to you during this past week, it can be specific to this week. It could be something from way back, you know, in the course. Whatever it is, just let me know and put it in there, record your random number, and we'll see how this all works out. It might be awesome, might be a disaster, who knows, but we will find out. All right, any questions on that? All right.
One suggestion not related to one another.
What was that?
If you have more than one suggestion not related to one another.
Sure.
Okay.
Yep, pop them in. And again, I will choose 5 for the vote. So hopefully I'll have to do that. I'm hoping to get more than 5 so that I actually have to, you know, think about which one of these, you know, should we tweet out. But yeah, definitely just let me know any ideas that you have, and we'll see how it goes. All right, so on to stats. So we just had our exam. So today is going to be a kind of light introduction to probability. It's one of the last pieces that we need in order to do inferential statistics. So you can see here we're on chapter 4, some key ingredients for inferential statistics probability. We are getting all those pieces together for the inferential statistics. And if you remember, inferential statistics, this is the super cool stuff where you can actually take psychological data, you can actually measure, you know, treatment outcomes, and then test whether or not those outcomes are real, so that work for a population, or are they flukes? So they were just a chance occurrence. So that idea of them being a chance occurrence is why we're looking at probability. So it's one of the last building blocks that we need. So we're still working on these basic skills. You're still on your journey. You're still painting that fence. But just to kind of give you a framework for understanding what it is that we're trying to do and why it's so important. Let's say that you graduate here and you start working as an educational psychologist. And let's say specifically that you're working with children on the autism spectrum. And you are studying a class, right? So you have a class of children. They're your students. Everybody's on the autism spectrum. And you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 students that are in your sample. 14 students on the autism spectrum that you have access to. And let's say that you come up with a new treatment, right? Let's say that maybe somebody suggested in an online anonymous survey, how about using tablets that are very interactive for your for your teaching. So you have this new treatment, and you're saying, you know what, that's a great idea. It's very interactive. It might hold their attention better. They can learn without having to make eye contact. It's sometimes difficult for children on the spectrum. Maybe this will improve learning outcomes. And let's say that at the end of the semester, you measure their learning outcomes, and lo and behold, it did. It improved their learning outcomes. Without inferential statistics, without the next step that we're building towards, this is where the story ends. All you could say, and this is literally all that you could say, is that we had this treatment of using tablets, and it worked for these 14 students. And if somebody called you up and said, oh, my son is on the autism spectrum, do you think maybe a tablet will work for him? Without inferential statistics, all you could say is, I don't know. There's no way to tell. I know for a fact it worked for my 14 students, but will it work for your son? I don't know. Will it work for these 2 children in another school? I don't know. Will it work for this child with that classic can stacking behavior that many autistic children have? I don't know. Will it work for this child who is playing alone rather than interacting with others? I don't know. Literally, you would only be able to say it's going to work for those 14 students. You would only be able to say that it worked for your students and not for the population of autistic children in general. So just imagine how useless psychology would be if that's all that it could do. It would either be completely useless or it would be reserved only for the very rich. So thank goodness that we have inferential statistics where we can take a look at a sample. We can take a look at these 14 students and we can intelligently and ethically say whether or not that treatment will work for the population of children on the autism spectrum, or was that treatment a fluke and only worked for these 14 individuals? So inferential statistics is really where the power of psychology to help people comes from. Because without it, we could help 14 people. With it, we could help millions of children instead. So that's what we're building towards. We got a few more pieces we got to put into the puzzle, a few more skills we need to develop. And one of them we're going to develop today, which is the introduction to probability. So we're going to introduce probability. We're going to change the way you think about probability. We're going to make you think about probability not as fractions, not as decimals. We're going to think about it as a frequency distribution. And then we're going to take a look at one of the most common frequency distributions in our universe, which is the normal curve. All right, so probability. So for outcomes, this is probably the way that you've been taught probability prior to this class. If you've seen it in math class, you've probably seen it in this formulation. Probability equals the number of successful outcomes divided by all possible outcomes. So if you are flipping a coin and you win when it's heads, there's one successful outcome, which is heads. There's 2 possible outcomes, heads and tails. That's why it's 1 out of 2 or 50-50. If you're playing with dice and you win when you roll a 6, there's 1 successful outcome, rolling a 6. There's 6 possible outcomes, 1, 2, 3, 4, 5, 6. So you have a 1 in 6 chance, 17% I believe, chance of success. So that's the way that you've probably been taught probability. Probability is so important in statistics. It gets its own little symbol. It gets that P, and that is the p-value that psychologists and researchers will talk about all the time. So I've already mentioned that important p-value. The p-value, oh, how's your p-value? Oh, my p-value was greater than 0.05. Oh, no, I'm so sorry to hear about your p-value. What about your p-value? Oh, my p-value was less than 0.001. Oh, wow, that's a good p-value. You'll hear psychologists talk like that. This is the p-value that they're talking about, that probability. Now, probabilities, and this is the change in thinking that hopefully we'll arrive at today, probabilities are equivalent to proportions. So when you think about probabilities, as a statistician, you want to start thinking about proportions. You want to start thinking about pieces of something. And we're going to see exactly what that something is in just a bit. So just to kind of make sure that you're clear on all of the terminology, in general, probability is written in this way. You'll also occasionally see it written this way, where it's the probability of a specific occurrence happening. So if you ever see, well, first off, we'll start here. If you ever see P, until you become one of those psychologists talking about your p-values, you can call that probability. And then this is the probability of A occurring. So when you have something in brackets, it's just a short way of writing the probability of this happening. What's the probability of A occurring? So if A is rolling a 6, what's the probability of a 6 occurring? If A is flipping heads, what's the probability of heads occurring? That is this terminology right there. We're not going to see that one very much. We're going to mostly see this one, but just so that you're aware if they come across it. All right, so probabilities and frequency distributions. We mentioned that probabilities are going to be proportions. What are they proportions of? They're going to be proportions of frequency distributions. So once again, you can see how all of the concepts that we've learned so far are being built upon in order to tackle these new concepts. So we're going to do the classic analysis here, and we're going to take a look at frequency distributions for dice roll outcomes. And this is one of the ways that theories of probability were first developed. And you might, just as a bit of a historical background, you might read about so-called Monte Carlo experiments. And they still do Monte Carlo experiments, but they are so named because they began when people tried to understand the probability of gambling games. They tried to understand the probability of casino games like roulette, like blackjack, like baccarat, and they didn't have the mathematical abilities or, back in those days, the computer software in order to simulate this, to figure out this probability. So what they did is they would go to Monte Carlo and they would just watch, and they would watch a roulette table and they would record which numbers came up. How often was it red? How often was it black? They would go to a blackjack table and record how many times did you bust on 16? How many times did you bust on 17? How many times did you bust on 18? They would go to the craps table and record how many times did a 7 come up? How many times did an 11 come up? And that idea of just taking a look at something and recording how often it happens is called that Monte Carlo experiment. So let's say that we did a Monte Carlo experiment. Let's say that we went to Monte Carlo and we were looking at die roll outcomes, so just to one die. What would we find? Well, we would, and I know this before we would even look, we would find that a 0 occurs 0 times. There's no way to roll a 0 on a 6-sided dice. You just can't do that. And let's say that we spent a long time there. We might record that a 1 was rolled 921,541 times. And we might record that a 2 was rolled 1,042,312 times. And we would record how often a 3 occurred, and a 4 occurred, and a 5 occurred. You would never get a 7, right? You can't roll a 7 with just the one dice. So those would be the actual frequencies that we would have observed. Now those numbers are very difficult to deal with. They're kind of hard to deal with. So what we're going to do is we're going to simplify this, not as the actual frequencies that we observed, but what we would expect should occur. And we can express that in this one here, which is the expected relative frequency. So for the expected relative frequency, we write a 1 for each outcome, each possible outcome, because each possible outcome is equally likely. So with fair dice, it's not going to be exactly the same, but in the long run, each of those is going to be equally likely. So that's what we're writing here. So you can think of this in terms of if we rolled the dice 6 times, we would expect a 1 to come up once. We would expect a 2 to come up once. We would expect a 3 to come up once, and so on and so forth. So those are the expected relative frequencies that we would have. So far, so good? All right. Now let's take a look at those probabilities. So if we were to calculate probabilities from these frequencies, we have the outcomes here, and we have the P probability of it occurring here. And if you remember, the probability is the number of outcomes, number of successful outcomes divided by the total possible outcomes. So if we wanted to find out what's the probability of rolling a 0, well, that occurs with a frequency of 0. There are 6 possible occurrences. So 0 divided by 6 is 0. There's a 0% chance you're going to roll a 0. What about rolling a 1? Well, there's one way to roll a 1. There is one possible outcome that is a 1. So 1 divided by 6, the total possible outcomes, gives us 0.17. That means that we have a 17% chance of rolling a 1. On any single roll, we have a 17% chance of rolling a 1. And because this is a fair dice, or a fair die, we're going to find that for every single number. So there's only one way to roll a 2. So there's one outcome that is classified as being a 2 when you roll a 2. There's 6 possible outcomes, 17% chance to roll a 2. And so on and so forth, 17% chance for a 3, for a 4, for a 5, or for a 6, 0% chance for a 7. All right, so this is probably, once again, the way that you learned probability before. This is the mathematician's way of thinking about probability. What we're going to try to do is we're trying to shift that into thinking about probability as a statistician. And when statisticians think about probabilities, they think about frequency distributions. So rather than displaying the probability of each roll in this format, they would express the probability of each roll in this format. So this is a frequency distribution, and it is saying that there is no frequency that a 0 would occur. The expected frequency for a 1 is 1, the expected frequency for a 2 is 1, the expected frequency for rolling a 3 is 1. This would indicate to a statistician that your dice is fair and that a 1, 2, 3, 4, 5, and 6 all have equal probability of occurring. So this is the way that we're going to think about it. We're going to think about it in terms of frequency distributions. All right, so what benefit does this give us? What does this make it easier to do? Well, let's say that you were playing snakes and ladders, and you had the rule where you have to land on the last finish spot exactly, right? So you do that rule where if you roll too much, you kind of bounce back, outside of the finish line. So let's say that you're sitting there and you need to roll a 2 in order to win. What's the probability that you're going to win on the next roll of the dice? Well, we can take a look at these probabilities here and rather simply answer that question. We can say, well, there's one way to win. We roll a 2, and there's only one way to roll it, and there's 6 possibilities. So you got a 17% chance of rolling a 2 on your next turn. You got a 17% chance of winning the game on your next turn. For a statistician, they would say, all right, here is the frequency distribution of all the dice rolls, and the ones that are going to win it for us are those rolls right there. So what's the likelihood that we're going to win? It's this proportion. It's this blue area. What proportion of the entire area is this blue area? So we win if we're in the blue, we lose if we're in the red, and that blue area is 17% of that frequency distribution. The proportion of that distribution that is blue is 17%. That to a statistician lets us know that we have a 17% chance of winning on our next roll. All right, so far it's really bought us nothing. It's kind of easy one way, it's easy the other, straightforward one way, straightforward the other. But it's not always going to be so straightforward. So let's say that you're playing a different game, and in this game, every single time you roll an even number, you win. Every single time you roll an odd number, your opponent wins. What's the chance that you're going to win on any dice roll? Well, we know which numbers are going to be the winning numbers, right? So 2 is a winning number for you. 4 is a winning number for you. 6 is a winning number for you. But what do we do with these 17%? What is it that we're supposed to do with them? Are we supposed to add them all up? Are we supposed to multiply them all out? There's 3 of them. Do we raise them to the 3rd power? Do we just multiply them by 3? Are we supposed to divide by something? What do we do with this group of numbers? This is where it can get confusing. So if you're dealing with mathematics, you would sit there and going, what am I supposed to do with all these 17%? A statistician, on the other hand, taking a look at a frequency distribution, will say, well, I'm going to win when there's a 2, I'm going to win when there's a 4, I'm going to win when there's a 6. I'm going to win in those blue areas right there. So the proportion of the distribution that is blue is the proportion where I win. 50% of the distribution is blue, therefore I have a 50% chance of winning on any single roll. So it makes it more straightforward when you're dealing with some of these common areas where you have multiple outcomes. All right, any questions so far?
Wait, why did
Yeah.
you pick just those few on the slide before that?
Oh, on these ones here?
Yeah.
Oh, it's just a hypothetical game where you win if it's even and your opponent wins if it's odd. It's an incredibly boring game, but I guess if you're...
Would that be like a question, like how you would ask the question? Like a test?
Well, yeah, I mean, this would be if there was, I guess if there was a multiple choice question where there was 6 options and 3 of them were correct. It's a horrible multiple choice question, but...
Oh, okay.
Oh, but you mean like, would I ask it this way on a test?
Right.
No, we're not going to be doing it the mathematical way on a test.
Okay.
We're going to be doing it the proportional way on a test.
Okay.
Yeah. Because the mathematical way is not helpful for statistics. Okay. All right, so that was a pretty straightforward example, but let's make it a little bit more difficult here, or a little bit more intricate. Let's take a look at 2 dice. So what happens now if we put 2 dice into this equation? So for 2 dice, let's take a look at the possible outcomes and their expected relative frequency. If you're rolling 2 dice, there's no way to roll a 1, right? That's impossible. If you're rolling 2 dice, 6-sided dice, there's no way to roll a 13. That's impossible. If you're rolling 2 dice, there's one way to roll a 2. You can roll a 1 on the first dice, 1 on the second dice. If you're rolling 2 dice, there's 2 ways to roll a 3. You can roll a 1 on the first dice, 2 on the second, or a 2 on the first, 1 on the second. So that's why that expected relative frequency is at a 2. The mode, let's bring that back. The mode outcome here is a 7. That's the most common outcome. Because you can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. There's 6 different ways to roll a 7. So you can see now we have different expected frequencies. We can calculate the probabilities of these once again using that mathematical formula. So once again, we can say the probability of a 1, there's 0 ways to do it. If you add up all of these, there are 36 possible outcomes when you're rolling 2 dice. So you got a 0% chance of rolling a 1. For a 2, there's only one way to roll a 2. You got to roll a 1 on the first, you got to roll a 1 on the second. There's only one way to do that. There are 36 possible outcomes. So there is 1 divided by 36 equals 0.03 or 3% chance that you're going to roll snake eyes, you're going to roll a 2. So if you're playing Monopoly, is everybody familiar with Monopoly? If you're playing Monopoly and you land on Park Place, and you buy Park Place and Boardwalk is open, you got a 3% chance of landing on Boardwalk on your next turn. Not a very high probability. That's the hard lottery to win. All right, so probabilities, there they are for every single possible outcome. And you can see once again, 7 has the highest probability, 17% chance of actually occurring. So that's the mathematical probabilities. Statisticians, again, want to see this as a frequency distribution. That's the frequency distribution. So, once again, these are the outcomes. There is one way to roll a 2. There are 2 ways to roll a 3, 6 ways to roll a 6. The height of the bar indicates how many ways each one can occur. What is the expected frequency of each possible outcome? So now let's say that you are playing a game, and let's say that your mathematician friend has devised a game, and you can win on the next roll if you roll a prime number. Okay, so these games will never take off. But anyways, let's say that you got to roll a prime number in order to win. There are the prime numbers. You can roll a 2, you can roll a 3, you can roll a 5, you can roll a 7, you can roll a 11. What's the chances that you're going to get one of those numbers on your next roll? Again, difficult. Hard to know. Are you supposed to add them all up? Do you multiply by them? Do you add them up and then divide by 6? Do you take the average of these probabilities? What do you do? How do you figure out the probability of getting one of these outcomes? That's the mathematical way. Things get simplified when you use proportions. So if those are all the outcomes that are possible, so 100% of your outcomes are in this frequency distribution, those blue areas are the ones that you win in. Those blue areas are the prime number rolls. And what you need to figure out is what is the proportion of those blue areas to the entire frequency distribution. So again, we're thinking about what is the proportion, what is that blue area compared to the entire distribution. I'm just waiting for them. Nope, there they go. All right, and this gets even more and more complicated as we increase the number of dice. So, if you've ever played Yahtzee, then you've been rolling 5 dice for that particular game. What are the outcomes when you're rolling 5 dice? Well, there are 5 ways. Sorry, the outcome is of a 5. There's only one way to roll a 5. You got to roll a 1 on the first dice, 1 on the second, 1 on the third, 1 on the fourth, 1 on the fifth. There's only one way to roll a 5, just the one way. There are 735 ways to roll a 16. You can roll a 1 on the first dice, 1 on the second dice, 6 on the... No, I'm not going to go through all of them. But anyways, there's tons of combinations in order to roll different ones. You can go all the way up to 30. You can roll 5 6s, but there's only one way to do that. Very, very rare. That is a very difficult thing to try to analyze, but we can put it into a frequency distribution. And this frequency distribution is going to be a lot easier to deal with. Because if you wanted to know, if you were playing a game, and in order to win on the next one, on the next roll, you needed to roll a 12 or less. That is the probability that you're going to win on your next roll. This blue area compared to this entire area here, the proportion that is blue, that is the probability that you will roll, in this case, 12 or less. Or let's say that the reverse is true. Let's say that you have to roll, I believe it was 23 or more, then that is the proportion that you're interested in. So that is the proportion of the entire area that is the probability that you will win if you need to roll a 23, a 24, 25, 26, 27, 28, 29, or 30. And then sometimes in psychology especially, we're interested in both extremes. What's the chances that we're going to roll 23 or higher? Or what's the chances that we're going to roll 12 or lower? This is the probability of that is the proportion of that blue area of this entire frequency distribution. So all you have to do, it's very straightforward. It's very, it's right there. All you have to do is figure out what that proportion is. All right, now you're probably thinking, how do you do that? Right? So what we've been talking about is proportions is straightforward. When we were dealing with that just rectangular flat frequency distribution, figuring out the proportion of that, you could probably do it with high school math. This one, though, gets a little bit more complicated. Some frequency distributions get a little bit more complicated, like this one here. However, what we're going to find out is that this type of a frequency distribution happens in our universe over and over and over and over again. And because it's happened, people like Gauss and people like Laplace, I forgot Laplace's name, people like Gauss and people like Laplace and other statisticians with mathematical skills that I do not even want to think about right now, they have figured out everything that we need to know about this particular distribution. So they've already done the hard work, they've already done the heavy lifting, and all we need to know is two things. We need to know, one, that probabilities equal proportions, and then the second thing we need to know, and we're going to learn that next class, is how to find those proportions. And again, they have already calculated out all of those proportions, so all we're going to have to do is learn how to read those proportions. So understand that probabilities are proportions, and then understand how to read those proportions. And you can thank Gauss and Laplace and all those other mathematicians while you're doing it. Okay, so I mentioned that this happens over and over and over again in our universe. So we're going to wrap up today by taking a look at why. Why is this happening over and over again in our universe? And especially, why does this happen over and over again in psychology? And the importance of understanding that it does happen over and over again. So this type of a curve, you might have heard of it before. It's oftentimes called the bell curve. It happens so much in our universe. The other name that it has is the normal curve. So that is the normal curve. It's the curve that is normal in our universe. So the normal curve, it's a mathematical or theoretical distribution that just often occurs in nature. So here's a smoother normal curve so you can see it. This frequency distribution happens in our universe very, very, very often. If you had to pick what a frequency distribution might be, if you had to guess what a frequency distribution might be, if somebody came up to you and said, oh, I just measured the amount of time that Generation Z spends watching Friends on Netflix, what do you think that distribution is? You might say to yourself, well, I have no idea, but I'm going to guess it's normal. That's your best guess. It probably is going to be a normal distribution. So, why does it come up? Why does the normal distribution that I just showed you look like those 5 dice rolls? Why are the 2 of these almost identical? And why is many of the things that we look at on this normal curve? Well, the reason for it is because this is the frequency distribution that occurs when multiple random factors come together to form a single score. And multiple random factors coming together to form a single score happens very often in our universe. So I'll give you a visual example of what I mean by that. So this is a normal distribution, Gaussian curve, normal curve generator here. And what it is, it's a device where there's all these little steel balls in the top of the device, and when you spin it over, it's basically like one of those carnival games where you drop a disc and it goes along the pegs. And where these balls end up is the combination of many, many random factors. So you can see down there in the pegs, there's approximately 10 rows of pegs. So there is a 50-50 chance every single time that ball hits a peg. There's a 50-50 chance that it's going to go to the left. There's a 50-50 chance that it's going to go to the right. And then when it hits the next peg, there's a 50-50 chance that it's going to go to the left. There's a 50-50 chance that it's going to go to the right. And that happens 10 times. And what you see happening is that most of the balls will end up in the middle of the curve. That's why the frequency is so high for the normal curve. Because most balls will go to the left a couple of times, they'll go to the right a couple of times. So we'll end up somewhere in that middle section. Some of the balls are going to end up in the extremes. So the balls that end up over here, these are the ones that went right every single time. These are the ones that went right 9 times out of 10. These are the ones that went right 8 times out of 10. And that's very rare. That's like flipping 10 heads in a row. It's not going to occur very often. And that's reflected by the low frequency of balls that came to this location. Same thing with the ones over here. If you're going to end up over here, you have to go left 10 times. You have to flip tails 10 times in a row. Not going to happen very often. So this normal curve happens in our universe over and over and over again because most things in our universe are the combination of random factors. Most things in our universe are the combination of different things occurring and then that contributing to one final outcome. So that's why rolling 5 dice looks like a normal curve. Its frequency looks like a normal curve because the outcomes here are the combination of 5 random factors. It's a combination of what did you roll on your first dice, what did you roll on your second, what did you roll on your third, and so on. 5 random factors. Most outcomes are going to end up in the middle. Very few outcomes are going to end up super high. Very few outcomes are going to end up super low. You get this normal curve. So we're going to end today with an important public service announcement about why it's vital to know that this occurs when many random factors combine to form a single score. And it's important to remember this because oftentimes our brains will go to the single most obvious random factor that we can think of and think that that's the reason for the curve. Anytime you see a normal curve, know that it is the cause of multiple random factors all coming together. So take a look at a few examples of that to close up today's class. So you probably all, I think it's a requirement, I'm from Canada, I'm not too sure, but you've all taken the SATs?
Yes.
Yes, okay. SAT scores are on a normal curve. So if you take a look at the SAT scores, 2010, you'll notice that very similar pattern. It is on a normal curve. This means that SAT scores measure multiple random factors. Most people think, well, you know, an SAT score that measures intelligence. Or maybe it measures, well, it will measure intelligence. That's part of what it measures. But it also measures how good was the school that you went to. It also measures how involved were your parents. It also measures, did you have tutors? It also measures, did you have proper diet when you were a child? So your cognitive abilities are at their maximum potential. It measures many, many different things. And this is one of the reasons why, I'm not sure if you might be aware of this, but this came out earlier this year in May. The SAT is starting to assign students an adversity score in order to capture some of these other random factors. So did you come from a disadvantaged economic background? Right? Were you low in socioeconomic status, or were you high in socioeconomic status? Did you come from an excellent school district, or did you come from a poor school district? So they're starting to try to account for these multiple factors to get to the core of what the SAT is supposed to measure, which is, you know, your scholastic ability. So they recognize that it's multiple factors all coming together. It actually is multiple factors all coming together, and your brain should trigger that every single time you see a normal curve. So every single time you see a normal curve, you should think multiple factors cause this normal curve. I'll give you another example of normal curve. Height. Height is on a normal curve. Most people, so this is the distribution for women, and then this is the distribution for men. So men on average are taller, women on average are shorter. Average height for males, this would be about 5'10" there. I understand the metric. It's 174 centimeters. So, you know, it's weird. Even in Canada, where we use the metric system, we still use feet and inches, and we use pounds. I've never asked anybody their height, and they've said like, oh, I'm 165 centimeters. But anyways, average height for males, average height for females. But notice, both of them are on a normal curve. Most people near the average, few people in the extremes, and that's because height is from a multiple number of random factors. So there is the genetic factors for sure. So when I look this up, what are the factors that attribute or cause height? There is definitely the genetic factor. So they estimate between 60 to 80% of a person's height is determined by their genetic code. But what other things factor into this? What other things are causing this normal curve? Well, a balanced diet is important for what height you would achieve. So if you have a poor diet as a child, doesn't matter what your genetics say, you're going to be shorter than if you had a balanced diet as a child. Use of supplements. So apparently some supplements can cause increases in growth or decreases in your height. Getting the right amount of sleep. Who knew? Sleep is going to affect your height. So if you got the proper amount of sleep every single day, you're going to end up being taller than if you did not get the proper amount of sleep every single day. Staying active, having proper exercise, avoiding injury is another big one. These are all factors that contribute to height. Practicing good posture, actually standing up straight, will over the long run make you taller. So it actually allows your bones in your body to grow to the height that it was programmed to. And then other things like yoga, or just that idea of stretching, staying flexible, maintaining good health, those will also contribute. So when you take a look at any normal distribution, once again, remember that it's a multitude of factors. And this is the case even if you see a difference between two distributions. So this one here, the difference between women and the difference between men, part of that is genetic, for sure. Part of that is just a genetic difference between males and females. But part of that could also be because of any of those other factors. So if it is the case that men exercise more than women, if it is the case that young children are more, young boys are more encouraged to go into sports than women are, part of that difference could be attributed to that factor. If it's the case that boys get more injured or more sick when they're children, that would decrease the difference, right? So maybe men would be out here if that wasn't the case. Any difference there could be due to multiple factors. And that's something that's very important to understand, because you will see data that looks like this. So this was the IQ distribution from IQ tests for black individuals and white individuals when they took the IQ test. And this has been known for a while. This was back in 1979, I think, is when they first had access to this data. So in this frequency distribution here, so we got a frequency distribution for black individuals and their IQ score. We got a frequency distribution for white individuals and their IQ scores. And clearly, we have a discrepancy here. There's a gap between those two distributions. So many people, when they saw this, jumped to the conclusion that it's a genetic thing, that's the difference is based on the genetics of the two different populations. That it's got to be a genetic thing, that's just the way that these two races are. And interestingly, they usually leave out the final normal curve, which is the Asian distribution, which is actually the highest one. So a lot of people just jump to it's genetics. That's just what it is. And once it's genetics, that's all you can do, right? We can't do anything about genetics. We can't alleviate this or change this situation if it's genetics, right? We just can't, we're not Jurassic Park. We don't have the ability to mess with that genetic code. But as psychologists, we need to look at this and we need to say, you know what? This is an issue, but there's multiple random factors. It's a normal curve. There are multiple random factors. And when you look up what actually contributes to IQ scores, yes, there is a genetic, there's a genetic component, but other things that contribute to them are factors like education. So you start taking a look and saying, do these two populations have the same educational opportunities? If not, that could close the gap. Things like nutrition. Do these two populations have access to the same nutrition? You start getting into socioeconomic issues. If not, that would be a way to lessen the gap. Drug and alcohol abuse. Is there a difference in these two populations due to socioeconomic pressure because of that? Mental illness that probably leads to the drug and alcohol abuse. Other diseases, healthcare, things that we can change, things that we can affect. So it's very important to remember this. When you see a normal curve, it's a multitude of random factors. And our human brains always want to go to one explanation. We love that one explanation. And you'll remember in the beginning of this course, a lot of what we started in descriptive statistics was taking a whole bunch of stuff and giving you one number, because that's the way our minds work. We need to understand as psychologists, anytime you see that normal curve, multiple random factors, we can't allow our minds to just jump to that one conclusion. All right, any questions about the normal curve, multiple random factors before we wrap it up for today? All right, so just a reminder, there was nothing due for today, so I'll just remind everybody again that you want to get 100% on your pretest points if you haven't already. We got the quiz me option, so as you start doing your Chapter 4 pretest, just be aware that if you're, especially now when things are starting to get a little bit more chained together, you might struggle a bit more on the pretest. Two things to keep in mind. Number one, the struggle will pay off. So wrestling with it, getting it wrong. There are studies that have shown that students increase their learning outcomes, even on the questions they get wrong in a pretest, as well as the questions they get right. So getting it wrong has value. So don't give up on the pretest, continue to do them, continue to paint that fence, but don't let it cause you any anxiety, because even if you're struggling on a pretest, just know that you can do the mastery points to get that pretest up to 100%, so it's not going to impact your grade at all. Also, if you are concerned about your grade, I will be grading the exams as soon as I can. And if after you see your grade for the exam, if you are concerned, two things to remember. Number one, the sliding scale for the exams. So this is probably going to be your worst exam. I've only ever seen students improve. I've never ever seen students lose the story. So if you got 100% on the exam, congratulations, keep doing what you're doing. If not, we'll see what we need to do in order to change and get you on top. But just know that that's why I have the sliding scale, so you won't be too detrimentally affected by your grade. It'll minimize that impact. And also 2 bonus point opportunities that you can jump on. So consider doing those as well. All right, if there's no final questions, that is it. That's all that I wanted to cover for today. So if you want to call it an early day, I don't know if we have anything to practice today, feel free to head on out. But if you have any questions about anything, call me over and I will give you a hand. But that is it.